Now,
So these build hashes are, I mean, they are only valid on your machine, let's say, right? You cannot put them in a build that is...
no, they're valid everywhere, because what they hash are other hashes, right? The commit IDs on Git, those are, you know, constant for the whole world. They hash the build options, okay, which are things like C flags equals -L whatever. That's again constant for everybody. You can check that out of Git. And they also hash the actual source for that specific package. Okay, so it is not a hash of the binary output. Okay, which is, you know, so there is room for some issues there, but that's the kind of the general way to do it, is to hash the inputs.
Yeah.
That's the thing that should be should describe a unique output.
Okay, so the files inside these directories are only valid for your machine. You cannot put them into another machine and hope it will work.
You can, but not in general, right? If you have a Linux machine, I can share my build cache with you, and when you run hit build and it goes to say, it computes the hash and says, I need this IPython artifact. If you pointed to my build cache, it would go get that, right? And you could try to use that. Now, it could be a problem if you tried that on an OS X. You pointed an OS X machine to a Linux machine, and they happen to hash to the same hash. That'd be a problem. But this is we're in the process of making these build artifacts relocatable, so that you can share them across machines and change their locations on a particular machine. And this is one of the things that has a potential big impact on HPC machines, because you might have your core group of 5 or 6 developers who are working on a particular machine, and if you can share your build artifact caches, then you speed up the build for all of your team by sharing those things.
You shouldn't have these issues with, for instance, different processors or different size of RAM or whatever that might make a difference on the build of it.
Yeah, I mean, those are potential problems, and that's not really encoded in the hash by necessity, right? That you would say somewhere in the build inputs say this is for this particular processor with this many parts of RAM. You could do that, and then you could fix that. But the sharing of the build artifacts is a tricky thing. But again, we're working on it. It's in progress. Okay, I need to wrap it up because I don't want to take any more of Kevin's time, but I do want to show you, what it looks like on your side as a developer. Okay, so my software is called Proteus. It's a Python package, which is very dirty at the moment, but I build a stack for Proteus, and the different versions of the Proteus stack are in here. So I've got Proteus.Linux 2, I've got Proteus.Darwin, Proteus.Cygwin, Proteus.Garnet. That's an HPC machine that we build on, and then a couple of other ones. But right now we're saving our different closely related versions of the Proteus stack are just stored in this example directory. But the one for this machine I've copied over into default.yaml. And so this is what a scientific distribution looks like to support Proteus. First of all, in this case, it extends a sort of a generic Debian software stack that kind of helps me out with setting up some defaults. And then it has a bunch of packages that Proteus depends on. CMake, because of course downstream some packages need CMake in order to build. Python, BLAS, a DAE solver. In this case, we go ahead and build impitch instead of using the system MPI, HDF5, on and on. Some of these things are, you can see that they're parameterized. So the Python dependency, we say, we don't want to use a host Python. We want to actually build using the python.yaml packages that builds our own Python. The PETC build we give it some more parameters at this point. We say we're going to go ahead and let Petsy build Parmetas using its own build system, and we're going to let it build a couple of these other linear solver packages that it needs for itself, right? In the long run, we'd like to invert that so that these dependencies are all Hashdist packages, but in the short run, we're flexible. We can work with using other people's build systems to get where we need to be. The rest of these things are just sort of straightforward packages in Hashdist. So what do those packages look like? So IPython is a very simple Python, well, I shouldn't say that. It's not a simple Python package. They've done a very good job with their build system. It doesn't need a lot of instructions. All we need to do with IPython is say, here are the dependencies. So we want to build the whole IPython notebook infrastructure. So we've got PyZMQ, Tornado, Jinja2, Pigment, Sphinx. Those are now going to be part of the stack. Okay, they're not in my explicit top-level stack definition because there I'm trying to specify what do I need for Proteus, right? I'm thinking about what Proteus needs. Here, because Proteus needs IPython, IPython's now adding to it and declaring IPython needs these things. So now the stack is extending. The other thing is, again, it points to the source. In this case, it's a URL, but it's a GitHub URL. So the key is a git commit ID. Okay? So, for example, let's see. Let's say we want to go back to that one. So what that did is hit build. It went to go, the default.yaml said build this stack, went down to IPython, went and looked in the IPython package description and said, we haven't built this version of IPython yet because that nobody, we had not, we just changed the commit ID there. We changed the source hash. So again, we've got all these input variables. One of those happens to be the upstream dependency hashes. And so now IPython had to be rebuilt. And now there's a new version of IPython sitting in, well, you don't see the output here, but if we look in that .hashdist/build directory, you'll see a new build artifact for IPython. Now, I say I try that out, I don't like it, it breaks my stuff. I go back to my version control and I say git checkout packages IPython. Oops. So I just reverted that change to the package description. I went back to the old commit ID that I liked. So it doesn't do anything, that's already there. Okay. So that's that kind of instantaneous rollback functionality. Then the last thing would be this sort of virtual ends type capability where we want to actually we're not just defining distributions that we go and expect people to use. We're also having sort of a virtual end type environment where you can do development of your new packages that aren't yet part of Hashdist or any distribution. And so there's this hit develop command, which I'm not going to run for us, but it hit develop profile name, profile directory name. Okay, so in this case, I do that for Proteus because I'm developing Proteus, and I don't, at this point, I want to make changes, rebuild Proteus, and just have them run in the Python environment. I don't want to update the build artifact of Proteus. And so if I look in this Linux, this is the output of the hit develop command. It looks like a prefix directory, like user lib or user local lib. In this case, it's Proteus /Linux2, but it's got a lib directory, bin directory, man, share, all the things that normally live in an install prefix. But they're all, for the most part, links to specific build artifacts that live in the Hashdist build artifact cache. Okay, and so there's a fair amount of hard work that went into making it so that this development directory, this prefix, it acts just like a hard installed stateful prefix directory. You can build stuff in there, and as long as, you know, like using auto tools where you do configure -- prefix equals, you give it one of these development profile directories and it will work. Okay, and things can link to those libraries as if they lived in this directory, even though in fact the actual versions of these libraries are stored in our Hashdist build artifact cache database. So I better stop there. I think I hit most of my demos, but if you're interested, I'll be glad to show those later. So the status, the library and the command line interface, which is the HIT tool that I showed you a little bit of, that's up and running. And again, we're using it for Proteus. We're using it for some of our internal projects, some of the stuff that Kevin will show, the Rome's project. I believe we have a version for Clawpack now that's, I don't know if it's being used, but I know Aaron has set it up.
Working on something I haven't seen yet.
The Phoenix team is using it for their distribution, and then we have a couple of kind of nice, I mean, I've never really seen this happen being in the government, but it's sort of taken off open source wise, like there are mysterious people using it, and they're adding lots of packages, and we think one of them is in finance because he won't explain what he's doing. But the packages, they look like maybe they're geared towards kind of financial modeling or something like that. So it's growing in terms of the packages that are defined in there. It's also growing in terms of multiple platforms. So we are, for the Proteus stack, you know, we are our sort of hard OSs that we're really focusing on are Linux, OS X, and Cygwin for Windows. By the way, on the Windows side, we can do things full user installs. So this is the idea that many of our Corps of Engineers staff members, you know, they're given a Windows box that's locked down. But now we're in the position where we can give them our stack and they can run it without having root access, which is a big deal. And according to Aaron, William, Cygwin has improved a lot. So he did not want to do it and was resistant to, but when he went and explored it, it was actually a lot easier than he thought, and we've actually feel pretty successful with being able to get the stack ported over to Windows using Cygwin infrastructure. Again, we've got a pull request working on the relocatable builds, which is the question you had. So being able to share the build artifacts. Aaron has a proof of concept, and this really gets at the reproducibility angle, where you can write an IPython notebook, and at the top of that notebook, you just have a few lines that say, here's the stack that you need in order to run this IPython notebook. Now, when you give that notebook to somebody else, when they run it, if you don't have that in your Hashdist cache, it goes out and builds it. Okay, and so the idea is that you've really made the IPython notebook, and I'm assuming you can do the same thing to some extent with a Sage notebook. You've made it a portable document that you can send to other people if they're willing to take the time to build the stack. Again, they don't have to do anything to build the stack except run the notebook and allow it to be built. So for example, for an IPython notebook that would build on Proteus, I could give it to you on a Linux machine or an OS X machine and say, here, you can run Proteus. You know, when you run it, it might take 2 hours to build the stack, but still you can reproduce that environment. And if you've already done it once, then it wouldn't, you know, it wouldn't take a few seconds. Another big thing on the horizon is flexible constraints. Right now, when we specify our, you know, when you specify your stack and you have upstream dependencies, that's pointing directly to a particular commit. And a lot of times the person who's building a general stack would like to just specify some constraints to say, you know, I don't need a specific commit of again, IPython, I'll just pick on it. I just say I need IPython greater than or equal to 2.0, and any hash of something greater than that will do. So working on that. And that's all. So again, I'll be glad to answer any questions now, and of course I'll be around for the rest of the week, so be happy to talk about it some more.
Questions? All right, let's thank Chris. So we'll switch over to Kevin's machine and then we'll start that talk in a minute or two.
talked about a half hour.
Or more.